Today we discuss about different types of establishment of different types of law like a Wiens law, Rayleigh-Jeans law, Wiens displacement law, and Stefan-Boltzmann law from the Planck's law of hypothesis or Planck's radiation formula. Okay, so in the last lecture we deduce the Planck's radiation formula and is expressed E lambda d lambda expressed by this equation lambda to the power 5 hc divided by e to the power hc by lambda kt minus 1 into d lambda. So this is our Planck's radiation formula. This is x to the power 5 lambda to the power 5, sorry, this is the value of lambda to the power 5. Okay, this is expressed as a lambda to the power 5. Okay, now the condition is to convert, so Planck's radiation formula reduces to Wiens formula when lambda tends to 0. Please note down, the Planck's radiation formula is reduced to or converted to Wiens formula when lambda tends to 0 and converted to Rayleigh-Jeans formula when lambda tends to infinity. So first of all, the condition is for a small temperature, for a very small temperature, lambda t is very small, first of one. So if lambda t is very small, then we say that e to the power hc by lambda kt, it is a very greater than 1 or very greater than 1. So from this equation we neglect this value of 1. So this equation can be expressed by e to the power hc, sorry, here is hc, yes, hc by lambda to the power 5 into e to the power minus hc by lambda kt. So this is the expression of Wiens formula. Okay, this is a very important, this is equation 1. So putting this value, putting this condition e to the power hc by lambda kt is very greater than 1 in this equation. So from this equation 1 we express this another equation which is called Wiens law. So what is the condition? The condition is very small temperature. The Planck's radiation formula is converted to Wiens law. Okay, now in the second condition, what is the second condition? The second condition is for a very large temperature. Okay, please note down, for a large temperature. Please note down, for a large temperature, that means where lambda, this value lambda t is very large. So if this value is very large, then this parameter e to the power hc by lambda kt is expressed by this equation 1 plus hc by lambda kt, 1 plus hc by lambda kt. Okay, so now putting this value in this equation, so what is the value of E lambda d lambda? The value of E lambda d lambda is 8 pi kt divided by lambda to the power 4 into d lambda. So this equation is a very important and also known as Rayleigh-Jeans formula. So what we can learn about? We learn that if temperature is very small, then this Planck's radiation formula is converted to Wiens formula, and when temperature is very large, then Planck's radiation formula is converted to what? Rayleigh-Jeans formula. Yes, Rayleigh-Jeans formula. Okay, so now in the next session we discuss about Wiens displacement formula, not Wiens formula, because in the earlier lecture we discussed about Wiens formula. This is the Wiens displacement law. So what is the concept? At lambda equals to lambda m, we know that E lambda is maximum. E lambda is maxima. We know that from the energy spectral density graph or intensity of energy distribution graph in the previous lecture. So how we will get this value E lambda is maximum? If this denominator term is minimum. So now we consider this value as a y lambda to the power 5 e to the power hc by lambda kt minus 1. So for minimum this value we differentiate this equation with respect to lambda and equal to 0, and after getting this differentiated and equal to 0 we get that e to the power minus hc by lambda m kt, this equation is equals to hc by 5 lambda m kt. So here we consider that these hc by lambda m kt parameter is equals to x So this equation can be write as e to the power minus x divided by x by 5. So students, this is not a very simple equation. This is not can be solved by the analytically. It is a transcendental equation, and it's only solved by graphically. So here two parts, left hand side is 1 minus e to the power x. So if we plot these two graphs separately, this graph look like this and x by 5 look like this, and if we merge the two graph in a single graph, then here one intersecting point where this x by 5 is intersect 1 minus e to the power minus x. So this value of x equal to 1.9651. okay, so now lambda mt equals to hc by kx. Where from this getting? Because we consider x equal to hc by lambda mkt. So from this equation lambda mt equal to hc by kx. So putting here the value of Planck constant, h, c is the speed of light, k equal to Boltzmann constant, and x equal to 4.9651. So we get 0.29 centimeter Kelvin. So this is the constant term. This is also known as Wiens displacement. And what is the value of Planck constant? The Planck constant value is 6.62 into 10 to the power minus 6.62 into 10 to the power minus 34. okay, m square kg by s. And what is the value of this Boltzmann constant k? This is a small k, Boltzmann constant. What is the value of k? The value is 1.38 into 10 to the power minus 23 m square kg s minus 2 k minus 1. okay, and last one, this is the speed of light. What is the value of speed of light? Everyone knows that 3 into 10 to the power 8 meter per second. okay, so putting all these value and convert this light speed of light in a centimeter. So putting this value all of here, and we get these values. okay, 0.29 centimeter Kelvin. So this is the Planck Wiens displacement formula. okay, now in the last part we discuss about Stefan-Boltzmann law from the Planck's black body. So what is the objective of Stefan-Boltzmann law? We measure the energy in the whole frequency spectrum. So this is the value of 8 pi h c cube 0 to infinity nu cube d nu divided by e to the power h nu by kt minus 1. Please note down, be carefully. This is the h Planck constant. This is the value of e nu, and d nu is the integration of 0 to infinity. So here put x equals to h nu by kt for the simplicity of this complex mathematical equation. Then we get dx equals to h d nu by kt. okay, so the term is 8 pi h this is 8 pi h divided by c cube kt by h whole to the power 4 from 0 to infinity x cube dx divided by e to the power x minus 1. So this is our mathematical form and integration of this part, and after some mathematical computation or to solve this integration okay properly, we get the value of energy E is equals to 8 pi k to the power 4 to the power 4 divided by h cube c cube. So putting all the parameters, pi to the power 4 by 15, this is the value of integration. So this is also expressed by a to the power 4, where a equals to this constant parameter 8 pi k to the power 4 t to the power 4 h cube c cube. These are 4. okay, this is t to the power 4, sorry, this is c cube, this is t to the power 4. okay, so this is a constant value, this is a constant value. okay, so now we calculate the rate. okay, now we calculate the rate at which energy is radiated per unit area of a black body at temperature capital T. So the radiate parameter is C into E by 4. So that means this value of E can be put here, E to the power 4 by 4. So where this is the also expressed by sigma to the power 4, but this sigma is equals to Ca by 4. So this is note down here. Okay, so this is what is the value of this R? This R is basically the rate at which the energy is radiated per unit area of a black body at a temperature capital T. So this is the establishment of Stefan-Boltzmann law from the Planck's radiation formula. So thank you. That's all about today.